So we're coming to you today with a video on linear approximations. And this is one of those applications with derivatives that you really get into when you start looking into engineering statistics and some courses maybe a little higher up. Um, we'll take a look at some what we mean later on and just as we look at some of these examples. But when we talk about a linear approximation, it's exactly what it means. Linear in terms of we're going to be using the equation of a line. An approximation in terms of we're going to be using that equation of a line to estimate a given value. Here's what I mean. Take a look in this first example. It says find the linear approximation of f of x equal 3 over x at x equal 4 and use the approximation to estimate 3 over 3.9. So you can just now that we have calculators and computer, I mean, we literally walk around with a computer in our hand. If you have a smartphone, you can just type in 3 divided by 3.9 and get an answer. However, yeah, if you're in a higher level math class, you're probably in there because you're headed towards some technical degree where you're going to be creating tools that do that. You're going to be designing tools that will do 3 divided by 3.9, right? Your job as engineering technology is to make life easier for those around you. So what we're going to do is talk about one of the ways in which we do this, one of the ways in which engineers and scientists make life easier for people. And one of those is using this linear approximation. So when we talk about the word approximation, you've got to be aware that it's not an exact value, right? And if it's not exact, that means there is an error involved. So one of the applications where you'll see these linear approximations come back up is later on when you do some type of engineering statistics where you're finding the percent error in some system that you're working with, okay? All we're going to do in this class is talk about how to find that linear approximation, and then we're going to use it to estimate. We'll leave those other applications to those later math classes and engineering classes that you may come in contact with later. Generally speaking, a linear approximation can be written like you see on the PowerPoint here. So the linear approximation L is equal to f of a at f prime of a times x minus a. Now you have to think about kind of what we're doing here. So when you have the equation of a line, it looks like this, right? Well, what you're doing is you're taking y equals y1 plus m times x minus x1. Right? This is something that you've seen before in other math classes. And that's really what we've got here. We've got L of x equal f of a plus f prime of a times x minus a. And we derive this from this point slope form of the equation of a line. So we're looking, when we say a, we're looking at a very particular x value. And then the function is known as the linearization. So you may see our linear approximations, you may see it referred to as the linearization of f at x equal a. Let's take a look at the first example. So we already looked at this briefly. We want to find the linear approximation of f of x equal 3 over x at x equal 4. So we can identify right off the bat that a is equal to 4. And if we use that formula for the linear approximation, we've got L of x equal to f of 4 plus f prime of 4. So this is where we want to spend a little bit of our time, finding the derivative at 4. So remember, the original function is 3 over x, or we could say 3x to the negative 1. And that makes f prime of x equal to negative 3x to the negative 2, or negative 3 over x squared, okay? So if I wanted to know f prime of 4, I'm going to plug 4 into this derivative. I get negative 3 over 16, and you can see that's negative 3 over 16. Now plugging that in is kind of where the PowerPoint's focused on. We're plugging that into the formula for the linearization. So 3/4, right? 3/4 comes from finding the function value at 4 minus 3 over 16x minus 4. Again, that a value is 4. we can estimate, so this is our linear approximation. Now we can estimate 3 over 3.9 if we plug 3.9 in as x, right? So x, right? We're going to plug 3.9, but we're going to plug that into our linearization. So we're going to have 3/4 minus 3/16 times 3.9 minus 4. Now you're probably going to work on the calculator a little bit, especially since you're looking at these decimals. 3.9 minus 4 is 0.1. And so on the calculator, you're going to type 3/4 minus 3/16. And that's where we're getting this decimal value. So I wanted to take a minute and show you what this looks like on a graph. Okay, so what you're looking at is a graph of 3 over x. And you can see that here. Okay, I've got my graph turned on 3 over x. We're going to go in just a minute, I'm going to turn on the linearization. But what we're focused on is this x value of 4. So this is an x value of 1, if you can see where my cursor is. 1, 2, 3, 4, and 5. And so what I want you to see is what happens at this x value of 4 when I turn this on. And you can see it really plainly here. Here's our x value of 4. This blue line is the tangent line at x equals 4. And the closer I zoom in, the more you can see, you're able to see that the blue line and the red curve approach one another. And the closer I zoom in, right, the closer you can see, wow, there's not much difference. We wanted to know what is the y value when x was 3.9. So the approximation, right, I'm traveling along the blue line, and that approximation gave me 0.7688. If I travel along the red line to 3.9, I get 0.7692. Those are very, very close. 0.7692 and 0.7688. So a very small error between what the blue tangent line is giving me and what the red curve is giving me. So the reason I wanted to show you the graph is because I wanted you to see that the linear approximation was the way we use our tangent line to estimate what's going on with the curve right here that we have. Here's another problem that's worked out similarly to the one that we just finished. I wanted to take a look at another one where we have maybe roots and powers involved. So this time we're looking at f of x equal to 1 plus x to the n. In the previous problem, we were looking at f of x equals n over x. Well, this time, the way we find our derivative is a little bit different. Let's take a look. So here we have f of x equal the square root of x. I'm still going to use that general rule, right? L of x equals f of x, well, f of a, right? F of a plus f prime of a times x minus a. So we're going to follow this rule when we do our linearization. And you can see f of 64, right, because we're looking at x equals 64. I need to find the derivative at 64. Recall that the square root of x can be written as x to the 1/4. Well, that would give us 1/4 x to the negative 3/4. So I can simplify a little more if I do, sorry, I did 1/4. Y'all please forgive me. I had a momentary lapse there, and I think my fraction made me think that was a 4. Let me start that over. F of x is going to equal x to the 1/2. I'm going to find the derivative by bringing the 1/2 down. I know you're probably sitting there thinking, I had no idea where 1/4 came from. X to the negative 1/2. So this is 1 over 2 square root of x. And so if we're finding the derivative at 64, we're going to take the square root of 64, which is 8, and 2 times 8 is 16. So 1 over 16 is our f prime. If we take just the square root of 64, that's where we get that 8. So our linearization turns into this equation here. 8 plus 1 over 16, x minus 64. I'm going to go in and I'm going to try to estimate 64.03. I'm plugging that into the linearization. 64.03 minus 64, right? That's 0.03 times 1/16. And then I'll add 8, And this is what I'm getting as that approximation. Now again, you can use your calculator to find the exact value, but we're just finding an approximation here, and so that works as our approximation. There's another one involving a power or a radical. Let's take a look at this one where we have f of x equal 1 plus x to the n. We want to use this to approximate 1.02 to the 2 power. So if I take the derivative of this thing, you have to remember that n is going to be some exponent, right? So the derivative is going to equal n times 1 plus x to the n minus 1 times the derivative of what's on the inside. And the derivative of what's on the inside here is just going to be 1. Now, we want to find the linearization at x equals 0. And that makes this problem a lot simpler for us, because if I have f prime of x equal n times 1 plus 0 to the n minus 1, well, this is just 1 to the n minus 1. And we know that 1 to a power is going to be 1. And then our linear approximation is just n. Our derivative here, f prime, is just n. So if you're looking at the linear approximation formula, right, our linearization, we have 1 plus n x minus 0. And we can simplify that to 1 plus nx. Okay. Well, this allows me to identify what n and x are. And in this problem, we wanted the linear approximation for 1.02. So that's going to be my x value. And n is going to equal 2. So when I plug this information in, I've got 1 plus 2. And then here it's 0.02. So let's talk about where the 0.02 comes from. We've got to have this 1 plus x, right? So I'm looking to figure out what is that. Excuse me. I'm looking right here, and I'm going to figure out what is this 1.02, right? So I've got 1 plus 2 times 0.02. Now, here's the thing. 1.02 comes from evaluating the function at 0.02. So if you're confused on where did the 1 go, right? 1.02 to the 2, if I do this, then I'm getting 1 plus 0.02 to the 2. Okay, so this is 1.02 to the 2. That's the real... That's the tricky part of this problem, is identifying that we're doing the linear approximation at 0.02. So this is where we're getting the 1.04. Here's a trig function, and I wanted to do this one because I've graphed this one out for you as well. It says find the linear approximation of f of x at cosine x, the linear approximation of cosine x at x equal pi over 6. So I'm going to use that to estimate 31 degrees. The linear approximation is going to be f of pi over 6 plus f prime pi over 6 x minus pi over 6. So let's talk about the derivative of cosine. That's negative sine. And so I need to evaluate negative sine pi over 6. Well, the negative sine of pi over 6 is going to be negative square root of 3 over 2. Excuse me, I had that wrong. I didn't look at my unit circle and it caught me off guard. The negative sine of pi over 6 is negative 1/2. Pi over 6 is this guy, right? And my y value is 1/2. Please pardon me, I did not look at the unit circle, and I should have. F of pi over 6 is going to be the cosine of that value, and that's the x value from the unit circle. So our linear approximation term is here, and we can evaluate that. If I go in, I can look at what is the cosine of 31 degrees. So this thing here, 31 pi over 180, that's how we convert an angle to radians. We take whatever that angle is, and we multiply it by pi and divide by 180. Now, when you do this, you're going to get 30 pi over 6. You're going to get, 30, this will turn into 30 pi over 180, because I have to get that common denominator. And so we're going to have square root of 3 over 2 minus 1/2. And what's tricky right here is when you look at pi over 6, when you multiply this by pi over 6, you're actually going to divide 3.14 by 6. Now, I would recommend that you use the pi function in your calculator to figure out what this pi over 6 is. Now, I mentioned I wanted to show you this on the graph real quick. So if I zoom back out and I show, I'm going to turn this one off and this one off. Here's cosine, all right? So I'm going to zoom in on cosine and I turn on that linear approximation, right? So here is our linear approximation, and you can see how at pi over 6, we're getting that blue and green line close to one another so that we can tell what that estimated value is, okay? As with all of these, if you have issues, reach out. I'll be glad to help you. If I went through this last problem a little too quickly for you, let me know, and I'll be glad to redo a video on this to help you out there.